Hello, Orrick here. I am going to do this practice test for Unit 10 on exponential functions and logarithms with video, and hopefully this is my second trial with this software, so hopefully this goes smoothly. I'll try to get started and keep this video as short as possible. I will post an answer key on our Google Classroom as well. So the first thing we did was graphing some exponential functions. Keep in mind here on question number 1, if the function or the number that's getting raised to an exponent, in this case 1.2, that's our growth factor, and if that number is bigger than 1, this will be a growth function. If that number is less than 1, the absolute value is less than 1, like our half-life problems where it's 0.5, then it's going to be an exponential decay function, and it'll be problems like our depreciation type problems. But this will be a growth function. On the calculator, I plugged in the function in the calculator, 3 times 1.2 to the x power minus 2, plotted some values. I clicked on second table. Here's some values. If you go a large negative number like negative 100, it's going to round it to negative 2. Basically, negative 2 is going to be our horizontal asymptote, and our range of this function will never get below negative 2. And the reason for that is this part of the function will never get below 0. If we put a negative exponent in, it's going to get smaller and smaller. We multiply it by a positive number, and it's going to stay above 0, and then we're going to subtract 2, so we're going to be a little bit above negative 2. Here's some values for the function. Negative 8, we are at negative 1.3. At negative 5, we're at negative 0.8. Negative 0.8. At negative 1, we're at positive 0.5. At 0, we're at 1, because 1.2 to the 0 is 1. Multiply it by 3, we'd be at 3, and then 3 minus 2 is 1. 2, we're at 2.3. And 5, we're at 5.5, and that's when it really starts to grow. At 10, we are off the graph, we're at 17. So the function is going to have a vertical asymptote right here. That probably should be a dotted line. And it's going to be at 0, we're going to be at 1. Negative 8, we're at negative 1.3, so we're down here. And if you plot these points at negative 1, we were at 0.5. Negative 5, we're at negative 0.8. So you can kind of see how this function is going to go. 2, we're at 2.3. And it grows. 1.2 is not like our doubling function where it's going to go up as fast, but it's still going to grow pretty fast. And so we get up here at 8, we're at, I think, just a little over 10. So our function is going to look something like this. And then it's going to really get steep. And it's going to stay above negative 2. The domain of this function is all real numbers. We can use any number for x, and the range is going to be y is going to stay greater than negative 2. And the equation of the horizontal asymptote is y is equal to that line at negative 2. Y equals negative 2. All right, there's our graphing problem. We do quite a few different types of growth equations here with simple interest, compounded interest, and compounded continuously interest. Here is a depreciation, a decay problem. That'll be the form, and you'll have a note sheet with the different formulas, but our amount that we're going to end up with is going to equal our starting amount, which is P on our notes, 5,200, That's our initial amount. And then it's going to be 1 minus the rate. 18% is 0.18. And for 5 years. So our t is up here. There's our equation. If our initial equation, that would just be a t and not a 5. Actually, I should probably put that on there. I'll erase that. And so there's our equation, and we could figure it out for any number of years. Once again, at 0, this parenthesis is 1, so 5,200 is our starting amount at t equals 0. And then we're going to end up with a value of our boat will be worth $1,927 when we're done. 1927.85. We might as well bring it right down to the penny here. Okay, now we deposit 5,000 in the bank, so these equations really start looking the same. Our amount's going to be equal to the amount we start with, which is 5,000. And it's simple interest on this one. And I'm using my mouse, so pardon my 3rd grade handwriting here. Now be careful on interest rates. 6.5%, 6.5% is 0.065. 0.06 is 6%, 0.065 is 6.5%. And that'll be to the t, and in this case we'll put in 6 for t. And we end up with $7,295, $72.95. If I did this right, correct me if I'm wrong, let me know. I probably won't redo the whole video though. And we'll move on to the next problem. And if you notice, we have 3 problems in a row that all start with $5,000. One is simple interest on the last one. This one's compounded interest. Really, our simple interest is compounded annually. So if you look at this formula for compound interest, n is equal to 1. So we have 1 plus r and 1 times t to the t power. But this one's going to be compounded quarterly. So n will equal 4 in this equation here. So the amount we're going to end up with. Now if you look at these that last problem and these next 2 problems, we're depositing $5,000 for the same amount of time at the same interest rate. And it's really to show you the difference in compounded interest. It's going to be higher. It's not going to be extremely higher. So if you get a number that's way higher, you probably did something wrong. So we started with 5,000. 1 plus our interest rate, which is 0.065. Now this time we divide our interest rate divided by n, which is 4, compounded quarterly, and then we're going to raise it to the 4 times however many years. So on your calculator, use 24 as your exponent. Don't, unless you have a calculator like this, when I figure that out, let me get out of there, 5,000, 1 plus 0.065 divided by 4, and I raise that to the 4 times 6. If you put 4 times 6, now this calculator I can do that because it keeps it up in the exponent, but if you have the older model calculator, you have to put that 4 times 6 in parentheses or just put 24. So in this one we get 73.61 and 79 cents. And our compound continuously. So now instead of compounded quarterly 4 times, it's actually getting compounded continuously, so more than daily. If you figured it out with this being 365 and did 365 times 6, it'll be probably within a penny of this same amount. But it's an easier equation. Your amount is equal to your starting amount, and it's P/E to the rate times time. And remember, E is just a number on your calculator. It's a little less than 3. It's about 2.718. I'll show you how to do this on the calculator. But we started with 5,000. E, and then I'm going to put this in parentheses because this one's a little bit harder to do in your head. 0.065 to the rate times the time times 6. That's multiplied. 0.065 times 6. And so you would do that like this. 5,000 E, which is right above the division symbol. Hit the second button and division symbol. And then I raise it to the exponent of, I'll put it in parentheses here, 0.065 times 6. It should be a little bit more than 7361, probably 7,400. Close, 7384.90. $7,384.90. Now, if you look at this next problem, same thing. We're starting with $5,000, but they're asking us to find t. How long is it going to take until we have 9,000? That's a dollar sign here. So it's going to be a little bit more than 6 years because we're only at 7,000 here after 6 years. In simple interest, we were at like 7,200 if I remember right. So our amount that we want to reach is going to be 9,000. Maybe I should change colors instead of keeping it black here. Equals our starting amount, 5,000. And it's simple interest, so just 1 plus the rate, 0.065. And we're trying to find t. How long? So first step is divide by 5,000. And 5,000 on both sides. And 1.065 is going to equal 9 divided by 5 is 1.8 equals, I'm going to combine this parenthesis, 1.065 to the t. And now to solve for t, we can rewrite this as a log. So to rewrite it as a log, it's log base 1.065 of 1.8, I'll put that in parentheses, equals t. And if we don't have log base 10, we can rewrite this as that's the change of base formula. So this is equal to log on your calculator, or you could use natural log of 1.8 divided by the log of 1.065. And like I said, it should be more than 6 years. It's not going to be way over 6 years. And if you do that on your calculator, log of 1.8 divided by log of 1.065 equals 9.333, 9.334, 9.334, and we're talking about years here. All right, we're cruising. Rewrite this as a log. So this would be log base E of 25. If you look at your formula sheet, this is all you have to do to rewrite a log, equals 3.219. And remember, log base E is the same as natural log. That's ln of, and that means, without putting an E there, that means log base E. So natural log of 25 equals 3.219. And if you notice on your calculator, here's your natural log, right underneath the log button. And if I do natural log of 25, that actually is the right answer, or pretty close. Write in exponential form, so to rewrite this, it's just 5 to the third power equals 125. Evaluate. So really on this one, this means 3 to what power question mark equals 2187. Now you probably don't know what that is off the top of your head. But to rewrite this change of base formula, we can do log of 2187 divided by log, and it's a log of any base. Now I just say log because it's on your calculator, and you can do log base 10. You could also use any base. You could do log base 7 of that whole thing. I'm going to use natural log on the calculator just to show you. 2187 divided by the natural log of 3. And that equals 7. So what that means is 3 to the 7th power is 2187. To rewrite this, 2 to the negative 6 equals x. So x equals 1 over 2 to the 6th power. And you can do that in your calculator. Otherwise, that's 64. 2 to the 6th is 64. So this x equals 1 over 64. And leave it as a fraction. It kind of shows the exponent power. Now, just so you remember this, 3 to the negative 3 is the same thing as 1 over 3 to the third. 1 over 3 to the positive 3. And so 3 to what power equals 1 over 27? Well, 3 to the third power is 27. So this is going to equal negative 3. Now, the other way to solve this, because we can do it the change of base again, we can do log of 1 over 27 divided by log of 3. But you might be able just to figure this out in your log of 3. You might be able to just figure that out without doing logs. If you notice that 1 over 27 is 3 to the negative 3 power. Okay, now to solve this, now you have to keep in mind your order of operations. So we want to get the log by itself, and then we want to get n by itself. So first we're going to subtract 8 from both sides, and log base 3 of n plus 1 equals 4. And now I can rewrite this as an exponent. This goes to 3 to the 4th power equals n plus 1. Well, 3 to the 4th power is 81. 81 equals n plus 1 and minus 1. So this looks like a complicated problem, but it's really not that bad. So n equals 80. You just have to do things in the right order. This one, 11 to what power equals 100? Obviously, it's not going to be a nice, easy number. 10 to the 2nd power is 100, but 11 is not going to be a nice, easy number. So we'll rewrite this as a log. This is log base 11 of 100 equals x. Solving for exponents, we use logs is really what it boils down to. And then we do the change of base rule. So we got log of 100, which is actually just 2, divided by log of 11. And I did this on the calculator earlier, x equals 1.9205. And the other thing about these kind of problems, when you get an x, put it in there, put 11 to 1.9205, and other than a little bit of rounding, it should equal 100. And it should be a little bit less than 2. 11 to the second power is 121, so we know it's a little less than 2. This one, we get the x by itself, minus 4 from both sides. 5 to the x power equals 25. Now you probably know that x is going to equal 2. But if it was a little more complicated problem, we would rewrite this as 5 to the x equals 5 to what power? And now x has to equal 2, if you notice that. And the last page here, natural log of 2x, so we'll rewrite this. I'm going to rewrite this as log base e, just so you remember natural log. Log base e of 2x equals 5. And now we'll rewrite this as an exponent, e to the 5th. Now, I know this gets complicated sometimes with that number e, but just remember e is a number just a little less than 3. It's sort of like 3 to the 5th is just a number, is equal to 2x. So you can divide by 2 right now, or do e to the 5th first, but x is going to equal e to the 5th divided by 2. We'll divide both sides by 2. And let's go ahead and do that. So here's my number e above the division sign, e to the 5th power, enter, and then I'll divide by 2. 74.206. I'll just put 74.21. 74.21. Same thing, you could plug it in for back into the equation, do the natural log of 74.21 times 2, and it should equal 5. And last property of exponents here, when you have two log equations that are equal and they're both the same base, 2x plus 7 has to equal 3x plus 1. When you get all said and done, if this comes out to be a negative number, then there's no solution. But this isn't one of those cases. So this ends up being a pretty simple problem. 2x plus 7 equals 3x plus 1. Subtract 2x from both sides and I get x. 2x minus 2x is 0. 2x minus 3x, I get 1x. And then subtract 1 from both sides and x equals 6. And if I plug 6 into this equation, I got 6 times 2 is 12, plus 7 is 19. And 6 times 3 is 18, plus 1 is 19. So log of 19 equals the log of 19. And the last problem is a bonus problem, but there is one like this on the final, so I wanted to make sure I put one of these in. And I don't have my formula sheet in front of me, but how I think of these problems is when it's a half-life problem, the decay rate is 0.5, so it's 1 minus 0.5, or just 0.5 as my decay factor. So my amount that I'm going to have, I start with 3, and then I'm going to go 0.5 for how long? Well, I'm going to go 8 days, and it's going to, every time period is 2.7 days. So every 2.7 days, it's going to cut in half. So 8 divided by 2.7 is really my time period in this. It's not years, it's not days, every 2.7 days it's going to get cut in half. And so after 8 days, I'm going to cut it in half by 8 divided by 2.7. So 8 divided by 2.7, 2.963. So about 3 time periods. And so if I do this, So I can put 2.963 here. And I have 3 times 0.5, the decay factor, raised to the 2.963, which was my answer. If I just put my answer in, I won't have to round. Second answer, and I'll end up with 0.385. So 0.385 milligrams. Which, you know, if you think about it, after 3 days, my 3 is going to turn to 1.5 after 2.7 days. After that, I'll be at about 0.75. And after that, if I did it one more time, I would be at half of 0.75, so about 0.38. And so you can see how this does work out. Here's my equation right here. And that would be T divided by my number of days of half-life. So, or 8 divided by my half-life was the, you know, general equation of the half-life type problems. So that's it. Ask me any questions in class, and we will hopefully do well on the test here coming up.